Let's find the interval of convergence for this particular series. We're going to start out with the ratio test. We have the limit as n approaches infinity of n plus 1, x to the n plus 1, and then over 4 to the n plus 1, and then we have n plus 1 squared plus 1. Then we're going to multiply that times, let's see, we have 4 to the n over n squared, or times n squared plus 1 over n x to the n. This is going to go to the limit as n approaches infinity of, let's see, we have n times n squared, which is going to be n to the third eventually if we multiplied it all out. N plus 1 times n squared plus 1. That's the n's on top. And then in the denominator, we'll also have n to the third. We'll have n times n plus 1 squared and then plus 1. Let's take care of the rest. We have an extra x on top, so there's an extra x up there. And then we have an extra 4 in the denominator. So we have 4 in the denominator. When we take the limit, we're going to get the absolute value of x over 4. That has to be less than 1. So negative 1 is less than x over 4 is less than 1. And then we get negative 4 is less than x is less than 4 when we multiply. Now certainly in between negative 4 and 4, the series is going to converge, but we need to check the endpoints. And it's like we're doing two brand new problems. Let's take the series, and we're going to plug negative 4 in for x. We have n equals 0 to infinity of n times negative 4 to the n over 4 to the n, and then times n squared plus 1. And when we take negative 4 divided by 4, we're going to get negative 1 to the n. So that's the sum as n goes from 0 to infinity of negative 1 to the n times n, and then over n squared plus 1. Now this is an alternating series. This is an alternating series. So we have the limit as n approaches infinity of n over n squared plus 1, and that is equal to 0. Then if we say f of x is equal to x over x squared plus 1, f prime of x is equal to bottom times derivative of the top minus top times derivative of the bottom, and that's all over the bottom squared. So x squared plus 1 squared. That's equal to x squared plus 1 minus 2x squared over x squared plus 1 squared, which is equal to, we have 1 minus x squared over x squared plus 1 squared. And the derivative, that will be less than 0 for sufficiently large values of x. As a matter of fact, x squared would have to be bigger than 1, so x has to be bigger than, well, 1. The series converges, so we say converges at x equals negative 4, and we say by alternating series test. There we go. So that's for x equals negative 4, but what about when x equals 4? Let's look at that series. We have n is equal to, n is going from 0 to infinity, of, we have n times 4 to the n, that's to the n over 4 to the n times n squared plus 1. And that's going to equal the series as n goes from 0 to infinity of, let's see, these are going to cancel out to be 1. So we have n over n squared plus 1. Let's compare this to, we have the sum as n goes from 0 to infinity of 1 over n. And this diverges. This is the harmonic series. So it diverges, and we have the limit as n approaches infinity of the absolute value of, I guess we don't really need absolute value if we don't have any x's. So we have n over n squared plus 1 over n, and that's going to be the limit as n approaches infinity of n squared over n squared plus 1, which is equal to 1. And since 1 is finite and positive, we have convergence. So at 4 converges by, we did limit comparison test. So the series converges on -4 to 4. The series converges at -4 at this endpoint, but does not converge at 4. We can also say, if we go back up to the top, we took the absolute value of all of this and then got to absolute value of x over 4 is less than 1. So the function is absolutely convergent from -4 to 4. So we can break this down and say we absolutely convergent on -4 to 4, and conditionally convergent at x equals -4.